Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, just a easy, casual video where I'm going to be taking a look at this 386SX motherboard. This was sent in by viewer Mike on Turbo Mail Call episode number 1. And I figured this week I need to do something simple because I still haven't finished cleaning up the basement so I can work on the Appalisa. So I figured this is a good diversion. The one thing about this 386 motherboard that I like is it's really small, as you can see. It's missing some parts though, so it's going to need some repair before this can work. So I don't know if this video is going to result in a working motherboard, but if it does, then I'm going to compare the performance of this to my usual bench 386SX that I typically use. This thing is pretty speedy and fast. It's 40 megahertz, but this one should be 40 megahertz as well. And I have a real soft spot in my heart for these little tiny, very inexpensive motherboards that came to be at the end of the life cycle of the 386SX. So I'd like to see this one working again. So without further ado, let's get to repairing this motherboard. So as I mentioned in the intro, I just adore these motherboards. I mean, look how tiny this thing is. It's as small as you can get for AT motherboards. We have one chip for the entire chipset, well, excluding the real-time clock, the BIOS, and the keyboard controller. There is a couple Jelly Bean Logic TTL chips, and of course we have the 386SX processor. And it is the AM386SX 40 megahertz. A little hard to read the markings there, but as far as I'm aware, this is the fastest 386SX that was ever made. There were other chips in this form factor which were faster. They were 46 SLCs and things like that, even clock doubled ones. They were crammed into that same form factor, and they gave you the advantage of having those additional 46 instructions. So you could run software that was written for 46s, even on motherboards that, for all intents and purposes, are much closer to 286 motherboards than a 46. And that's what I find fascinating about these motherboards. They are a weird combination of 386 capabilities with the 386SX with a lot of 286 restrictions. 16 megabytes of memory maximum, almost always just ISA slots, no integrated peripherals, and of course you have the performance implication of only having a 16-bit bus coming out of the 386SX. That was the way that Intel really saved cost, mainly for the manufacturer of the motherboard, because you don't have all those additional address lines and data lines that the 386, the full 386 FAT has. This thing really has a similar structure to the 286, and that way a lot of designs for 286s could be adapted actually to work with the SX. The Intel 8286 came out in 1982, and that brought with it a 16-bit data bus, a full 16-bit data bus, not a multiplex one, and the ability to address up to 16 megabytes of RAM. That was pretty awesome for 1982. Well, when this particular motherboard came out, which was probably around 1993, in fact 9311 is the date code on the chipset here, the 286 was already 10 years old, and the 386 had already been out for a number of years. And of course, the 386, the full 386, was a huge upgrade over the 286 because it had a full 32-bit data bus, and it had an expanded address bus that could go up to 4 gigabytes of RAM. So it kind of blew away all the limitations of the 286. Of course, though, in 1993, a lot of people were okay with just a 16-bit data bus for, say, ISA cards or the slower RAM and a 16 megabyte limit. If you were just going to be running Windows 3.1, that was probably fine. But you also get the 386 instructions, the protected mode, and the virtual memory that the full FAT 386 supported while still having a very inexpensive system. So like I said, this motherboard really was the low end. Maybe there were 286 boards sold at this time in 93, but really I think this was generally the low end and yet offered quite good performance. Now you'll notice that this system uses an ALI chipset. I think this chipset was used pretty widely on lots of single board computers and plug-in cards that offered 386 capabilities. In fact, I think a later iteration that was like a one-chip solution that had a full computer, including a 386SX core, included this particular ALI chipset. But what I'm kind of curious about is if we can get this board working, my other 386SX, the one I usually use, which is also 40 megahertz, I might add, it has an MX chipset. And what's cool about this one is this chip has built-in 8K of high-speed cache memory, which will probably make, in addition to the fact that the chipset's very flexible with timing and stuff like that, I think this will be a faster solution than this motherboard, even at the same clock speed of 40 megahertz. Now, one thing this one has going for it, though, is it's just smaller. I mean, look at the size difference. That's pretty substantial, to be honest. And I think a lot of that's due to the fact that the chipset on here is actually made up of two chips. There's one that's under the speaker, while everything is just shoved down into that one ALI chip. Now I have a math code processor in here. Is that really needed? No, because hardly anything uses that, but I do have it, so it's installed in the system. Now this one doesn't even have a socket installed, but if we can get this working, I do have a replacement socket that I could put in there to give this the capability of running this math code processor. In addition, when Mike gave this to me, it's missing its power connector, which is weird. I don't know why. It's missing its battery, but that's fine because that's typical. These leak and a little bit of corrosion there. That pad is missing, although that might have happened actually when someone desoldered that. And then the other strange thing is that both of the oscillators are missing as well. Now, I'm not sure why it's got two, and we'll have to figure out which one of these is actually for the CPU. Sometimes there's the capability to run the math code processor at a different clock speed. It just depends on the chipset. But without a doubt, one of these is going to be required to run that system. So we're going to have to try to find photos or information about this board so we can hopefully look at a picture to see which one should be the one that is used. I suppose looking at the bottom of the board gives us some telltale signs that this is the one that was removed from the board. So almost certainly that's the one that's going to be needed. And the one over here, yep, it doesn't look like any work's been done, nor on the FPU socket. The proximity of the oscillator to the math code processor pretty much tells us that those are related. And then one of the other things about this board that isn't great is it doesn't really have any labels for what any of the jumpers are. Obviously these connectors are labeled, that's fine, but we have jumpers there and a bunch over here. And these aren't labeled. This will be for the battery, so an external battery, so that's not a problem. But some of these are concerning because obviously someone has removed parts from this board for one reason or another, and I'm wondering if someone has removed some of the jumpers. Also curious is we do have some solder pads on here for bridging. These are kind of a crude form of a jumper, potentially to add or alter functionality for the CPU. If you were using one of those 46 SLC chips in the same package, sometimes the signaling needs to be a little bit different on a couple of the extra pins, and it could be what those are for. And I must say the condition of this board overall looks quite good. I don't really see evidence of corrosion, and I don't know if Mike's cleaned this up, but you know, a lot of times the battery can leak and you get it on the slots or on these chips right here. That doesn't seem to be the case. And on the back side of the board, again, things look pretty good. Although I don't know how this thing was stored, so it'll probably benefit me to just give it a once over and look for any scratches, just in case there's any broken traces. But before I do that, I want to make sure my capture setup's working. This is what I always recommend doing when you're working on PC stuff. So let's get this thing all hooked up and test it. This is the video card we're going to be using. This is a Cirrus Logic GD5428. This thing's pretty fast because it runs in 0 weight states and it actually works in 0 weight state mode. And I'll be using this card for floppy and IDE. I've shown this off. Jared sent this in. What's interesting about this is it had some kind of a ROM on here originally. I just replaced it with XT IDE. I put a right angle connector so I can run my compact flash directly, and it made some small modifications. This is power that runs up to the adapter. And then these additional bodge wires are so I can tell when the floppy drive is being accessed. It actually turns on the yellow LED, and the red one is for hard drive activity. All right, here we go. Let's turn this thing on. Oh, I got to plug in the capture device. Otherwise, of course, that's not going to work. There we go. We're booting up. That's excellent. And I'm going to run some quick speed diagnostics and take a couple screenshots just so we can compare to the other one if I get that up and running. First one is, oops, wrong directory, speed 600. Right, 61.21 megahertz. That's the effective speed compared to an IBM PC AT. The original 5170 running at 1 weight state. If it was running at 6 megahertz, the CPU rating here would be around 6 megahertz. And then FPU speed is, well, it's a number. It's 114 megahertz, equivalent to what the original 286 IBM 5170, again, running its very slow floating point unit. It's running much, much, much faster. And then the video speed is 5228 characters per millisecond. That is very indicative of this card, which runs at 0 weight states. And then, of course, the AT bus on here is also sped up. I have it overclocked a little bit, and the cache memory is turned on. So overall, this board is running relatively quickly. And then we'll use this DOS program called Cache Check by Ray Van Tassel. And this will show us how much cache memory is available, if any, and how fast the memory is. And I do have the memory sort of tuned up on this board as fast as it can go in the BIOS before the system starts to become unstable. And as you test the memory, it has 8 megs installed. What you're looking at is the memory access block size. So we can tell right off the bat, without even the results, this has 8K of cache memory because the timing 53, 53, 53 is under the 1, 2, 4, and 8, and everything after that is slower. It's 93 all the way across, and that's microseconds per kilobyte. And when you read down below, it says the machine appears to have 1 cache. Well, yeah, it does. It just has the one built into the chipset. It's 8 kilobytes in size, and it's 20 megabytes per second, or 50 nanoseconds per byte. relatively fast, actually. Faster than this memory is that's on this board. I think it's probably 60 nanosecond memory. And then once you leave that cached memory block, so anything over 8K being read or written to the memory, the effective speed is about 89 nanoseconds per byte. Well, actually, that's the reading effective speed. And then you can see the access time for reading and write. But it does say that a RAM bank is 2 bytes wide. Well, remember, this is a 16-bit data bus on here. So yes, 2 bytes, that's 8 bits plus 8 bits for each read or write. I was going to say I was going to reboot the system and try to run Doom, but it looks like we have invalid command com. That is probably happening because I think I have the ISA bus overclocked a little bit too fast for this card. I got to say my old controller card didn't have any issues with overclocked bus, but the chips that are on here, the drivers and whatnot, they must not work that well. So I got to go in here and change the bus clock. So it's S clock divided by 4. So the original stock setting is divided by 5. So 40 megahertz divided by 5. 2, I think, is way too fast for this card. 3 was what I was running. It was a little corrupted. So we're going to try 4 and we'll run this again. And maybe I can, well, I was going to try to run another benchmark. Let's see if the system boots up. Yeah, it's running high mem. Ah, the system rebooted. So the problem might not be the bus speed. Actually, it might be fine at 3. It might be this read and write speed. So let's change it to 2 and 2 and see if that works better. Okay, that booted properly. So the bus speed is back to 40 megahertz divided by 3, so that's around like 13 megahertz or so, so it's definitely overclocked over the 8 megahertz, but I had to slow down the RAM timing a little bit. Let's rerun those benchmarks, and then we'll go on to working on this other motherboard. There is an auto config option in the BIOS, by the way, and if I ran that, things would just work fine. There wouldn't be any issues here. It's just I'm trying to extract all the additional speed I can out of this. All right, so changing the RAM speed didn't seem to have any effect here. So the memory access block size times, that's all the same. It's 53 and 93, just like it was before. But what has changed is the effective RAM access time for writing. It used to be 77 nanoseconds, and now it's 102. Oddly enough, though, all the other metrics are exactly the same. It's only that effective RAM write time that has slowed down a little bit. What are the ramifications for slowing it down? I don't know. Maybe in a game or something there would be a bit of a slowdown, but obviously we weren't stable before, so I think this is what we kind of have to do. For a little game benchmarking, I'm just going to use fast Doom. Game just standing still on the beginning level of Doom, and we're running at 13 frames per second, and that's with the detail level set to low. If we change the detail, well, we go to potato, we can go to high detail, and it really takes a big hit on this particular system. But I feel like going to flat visplane rendering, which are the floor and ceilings, and low detail, gives you a somewhat playable frame rate. It's not too bad. You can kind of see here, we're actually hitting, into the high 20s. So it's not bad at all. And if I had this system, I would totally be using these settings. Now let's try these demos. I don't know if these actually work, these time demos. Let's see. Yeah, this actually does work. Okay, cool. So we can actually have a direct apples to apples comparison between this motherboard and this other one. There we are. Fast Doom actually calculates the frame per second. So 17.046. I will save that and we will test on the other one. So, can I get this board working? Well, let's give it a little bit of an inspection first. It's always good to start up in this battery leakage area. Looks like a little bit of rework has been done on that resistor. Everything else looks pretty good. It doesn't really look like there was much leakage on here, if any, because things are relatively shiny and looking normal. Here's our little 32 kilohertz oscillator for the real-time clock chip. System BIOS is pretty curious. New image technologies? I am unfamiliar with them. I'll be curious to see what this is, and if this board doesn't even work, I will definitely dump that. The main ALI chip that runs the whole board, everything looks good. I don't see any bad or bent pins. 36SX, same thing. Everything's looking pretty good. It's slightly dusty, but generally in really good, clean shape, actually. So this is really one of the only identifiers on this board, 200-03-690-330-2. It's nice that these memory sockets have metal clips, not the type that break really easily. On the back of the board, looks like a little bit of rework has been done with that component. That is a fuse. And those can definitely go bad. If your keyboard's not working and it's not getting 5 volts, that could be it. You can just jump over that if you don't care about having a fuse there. So what's curious to me is there aren't a lot of telltale signs that a power connector was ever actually on this board. These pads just look really, really clean. I mean, there's obviously some evidence that some solder was there, but I don't know. It just doesn't look as kind of gummed up as I would expect for something that was installed and then desoldered at some point in the past. Now you notice these pins in the middle don't seem to go to anything. There's nothing on the top side. And on the bottom side, nothing on the bottom side, and that's just because this is a multi-layer PCB and the ground plane is in the middle. Now really what I need to do is just sort of look for any shorted connections, like if these pins were bent over and maybe touching something else, or any kind of traces that were broken. Now you're watching on video, you might be able to see stuff that I don't, but right away everything looks fine. Looks like a date code there, 1993, 9th week. Everything on the ISA slots on the bottom side looks fine. Kind of some scratches there, evidence of it, but it hasn't really gone through anything. There's our rework for that crystal oscillator that was removed at some point, but everything on these traces looks fine. The FPU socket doesn't have any signs of rework, so I really don't think anything was ever installed in that position. Just look at the memory modules, everything looks fine, and I really don't see signs of corrosion from the battery leakage. Pretty amazing. Okay, well, I'm not seeing any issues besides the fact that we can't power this up without the power connector and the oscillator. So for the oscillator, I'm just going to install one of these sockets into that position. Obviously, this is a normal IC socket, so I'm going to have to remove all these middle pins and just have the 4 outside pins. But then that'll allow me to try, all sorts of various crystals that I have sitting here. And then for the power connector, I don't have any extra power connectors. So what I like to do is I keep a little stash of junk motherboards that I steal parts off of, and this one has a perfectly good power connector right there. And you can see that I've stolen lots of parts off this thing. In fact, all these slots are missing and some chips and stuff. And yeah, the way I got these out, notice a little bit of darkening there. I used a blowtorch to get this thing nice and hot, and I was out in my garage, of course, because it emits a bunch of terrible toxic smoke, and then I banged the motherboard onto a bucket, and a bunch of the components, all of these slot connectors, they just fell out all together. And I'm pretty sure I reused one of these slot connectors on some other motherboard that I needed to repair. Yeah. And you can tell by this large socket, this was a 386DX motherboard, a fat 386. The reason why this turned into a parts board is this board does not have any onboard RAM capability. It requires a RAM board that plugged into this position, and I didn't have that. So it became a parts board, and I needed parts, obviously, and I'm gonna take another part from this. And anything else I might need in the future, like DMA controllers or whatnot, here's a good source for them. Look at the delamination that was happening from the blowtorch. You can actually see the fiberglass that makes up the PCB on the inside. Pretty cool, huh? Let's give this the best chance of actually coming off. So I'm going to reflow all these connections first. I don't actually normally do this, but it can help for sure. Oh yeah, there's a lot of ability to absorb heat on this board, a lot. I didn't realize this was a 2-part connector. So there's one part. Oh no, I broke one of the pins off. Oh dear. And this one is still, oh no, that one came off. No broken pins on that one. Oh, that's annoying. I didn't even realize I did that. Well, it might be okay as long as it's one of the ground pins that is broken off. Okay, when we take a look at this, it's the middle 4 that are ground. Well, unfortunately, that did not work out for me. I wonder if I can swap these pins around. Oh, I might be able to move them. Yeah, because if I could just move that broken one, or just take it out entirely, and just put one of these good pins in that position, that might do the trick. Actually, and the important thing I need to look at is find some pictures of this, because I don't even know which way this goes on. I mean, I could probably figure it out by just toning it out, but yeah, these could go on either way, right? Oh, by the way, I just realized there are little keys to tell you which way these go on. So the little plastic peg there, so it goes on that way. They're a little bit melted, the pegs, but they'll still work. Okay, I have a set of these little things that should allow me to depin these, maybe. So I'm just gonna put this in a little vise so that I can try to wiggle this out. Oh, actually you do need to depin it. So hopefully I didn't damage the connector. I might have, and I'm just gonna have to figure it out. But see that lower little notch? I should have pushed a little thing up through there to push that in. Okay, I'm gonna do it with the other one. Okay, I'm not really explaining this properly, but I think this little pin here, if I push it in there, I feel like I've released it, I think. Just gently try to pull this out. Okay, it was hard, but I got the pin out. It's a bit mangled, but I think it should be okay, hopefully. There it is. I moved it over one position. So that means one of the ground pins is missing, but that doesn't really matter. All that matters, of course, is that I make sure that the missing pin is towards the middle, which is where the ground pins are, the 4 middle pins. Now, before I solder these in, I'm going to look for a picture of this motherboard because I just want to double check for sure that I have these in the correct orientation. I wouldn't want to put them in the wrong way and have to remove them again. Now, I did a little bit of searching on the retro web and I found this motherboard, and it looks exactly the same, at least the placement of all of the chips and things, especially the way the keyboard controller BIOS and the real-time clock are. Funny thing is, there are a bunch of variants of this board, clearly all made by the same company. Things are switched around slightly, but this one is very close. But then using this string of numbers that was on the motherboard, I found these, and this looks very, very similar. Now, the number's not exactly the same. The difference is on the motherboard I have, it's 330-2, and this is a 412. So must be a later revision of the board. But Miltronics, name of the company, and it's ALI, same chipset. It says 33 megahertz. And indeed, with the crystal at 66 megahertz and the chip saying 33, that definitely is a 33 megahertz one. But we have several photos to go off of. Yeah, let's see what this one is. This one's 80, so this is a 40 megahertz variant. Well, it's hard to read the number, but I'm assuming that's 40 megahertz because 80 megahertz. It's definitely running at 40 megahertz. And it is that later revision or different number, 412-6A, unlike the one I have, which is a 330-2. Should be similar enough, though. What I really want to see, of course, is the way the power connector is installed. So the tall edge of the power connector is toward the SIM sockets. Cool, so I think that means this should work. So I just need to kind of get these in the board a little bit better. Actually, they don't really go in very well because I cut, those little tabs are broken or, mangled. So I think I'll solder one pin on each and then I'll position them correctly and then we'll get them fully installed. All right, there we have it. We are reattached. Just have to clean that flux up, but these are on there solidly and should work totally fine with that missing pin. No problem. Okay, let's get all these pins out of this connector. So I just put this in the vise. What you can do is you can touch the soldering iron to the pin first before you put the pliers on it, because that will wick away the heat. And there's a socket perfectly suited to one of these oscillators. It will plug right into there. Now, one of these oscillators has a square corner versus round and a dot. That's pin 1. So when you put this socket into the board like so, you want to have the notch on the socket essentially the same direction as the pin 1, because that is pin 1 on a chip if we plug a chip into there. And check out the photos. So the crystal oscillator is right next to the CPU, and the one that would be near the math coprocessor is not installed. Before I prepare another socket for an oscillator, I want to make sure this motherboard actually works, because if this thing is not working, that's a bit of a problem. And one of the reasons why is when we look at documentation, there's nothing. No drivers, no documentation. There are a couple BIOSes on here. And incidentally, ALI, as far as I'm aware, is Acer or became Acer, the company that pretty much everyone knows these days. I think that's the same company. So we definitely don't have schematics for this board. We don't have any jumper settings. We can look at the photos, of course, so that's something. The problem is this ALI M1217 chipset, there's no documentation for this either. Now, I've done some searching and I found some purported data sheets for this chip, but the problem was they weren't for this chip. They were for some combo chip that has a built-in 386SX, and it doesn't have any technical information anyways. So it is not the information we need for these chips. Interesting that there's a rebadged version, a Biotech 82C3860. So there's the Biotech version. I didn't look to see if there were documentation for this Biotech chip, but no. Literally the only mention of it is retro web. So it's kind of problematic for us, because if this thing is not working and we need to do some more troubleshooting beyond looking for, bad traces or clock or something simple, well, we don't even know the pin out of the main chipset. That's highly problematic. Not having the schematics is one thing, but at least when you have the data sheet for the chips that make up the board, you can kind of figure yourself around. But this ALI chip has a lot of pins and no information on what anything is. Okay, let me solder this socket in here so we can get an oscillator on here and get this machine hopefully up and running. Well, and with that, theoretically, we have what we need to see if this thing runs. I'm just going to spend a moment to clean up the bench, and I'll get the power supply out and we'll give this a test. If you have a motherboard like this that you have no idea whether it works or not, you really need to get yourself one of these post analyzer cards. What this does is will show you the status of the voltage rails along with the ready signal, the reset signal, and the clock signal. But it also has a display. So if the BIOS is executing code, so the CPU is trying to do something, well, what it starts doing is writing to an I/O address, and this card supports these 3 I/O addresses, 80, 84, and 300 hex. And it will display whatever's written to it. So usually as the system starts to boot, it will start writing codes, and that gives you a good indicator the system is actually working. These are really inexpensive and highly recommend these. It also has a speaker on it, so you can plug these wires into the speaker connection, because often the speaker can tell you if something is unhappy before you even have post codes. Like if the RAM's not working, it can start beeping, for instance, and that'll do that even before it displays a code. So we just pop this into the board, and there is an indicator here to tell you if you're using the ISA connector, this is the rear of the motherboard. I have the main power on the power supply on, but this is off. This is the ATX power supply signal. So there's nothing coming to the board right now. We'd see these lights come on if it was going to work. Now, if I turn this thing on right now, it's not possible that it can work because we're missing the crystal oscillator. Actually, let's just give it a try. Whoa, try. Okay, we had a tantalum blow up. That freaked me out. Glad I had that on camera. It was this one right there. Maybe I should have spent a moment to check to see if those were shorted or not, but I didn't. So at least you got to see a little bit of magic smoke and a little freak out from me. Yeah. Okay, so we're gonna go on the ground pin. Just make sure we have ground on those middle pins. We do. And we're gonna check for shorts on these other pins. Now that's not a short, even though it's beeping, it needs to be near 0 ohms. That's just normal load, but probably it's like a 5-volt rail or something. 5 ohms is okay as well. You really are looking for the really low resistance. So 5 is fine. It seems kind of low. You might think that's not good, but generally that is not a problem. And just to demonstrate that, and maybe I'll be proven wrong, let's grab this other motherboard and we'll do the same test on this one. It's funny, this one's missing a bunch of tantalums here. I don't think I ever took them off. Okay, I'm on the ground pin. Okay, so interesting. This one doesn't do that. I know I've had motherboards that definitely did it, but this one is not one of those. That's the ground pin. That's fine. Yeah, we're getting, let's switch this out of continuity mode. It will give us a good indicator of what this motherboard is giving us. Oh, there we go. There's some K ohms there, 2.4. Your mileage may vary. I don't think what we're seeing on this one is a fault necessarily. Obviously, I think the 12-volt rail was probably shorted with that tantalum. Let's get that out of there and just give this another quick test. Yeah, this is lower than I would expect. So these are all shorted together. Let's just see what those are. So between ground and red, which is 5 volts, we're getting like that 5 ohms. Okay, and then whatever the blue wire is, that one's 65 mega ohms. That might be the power good signal. Then there's brown, yellow, white, and there's another red cable. So the red cable will be also 5 ohms. So I think this was red here. Yeah, 6 ohms, whatever. Okay, so this is yellow, 12 volts. And then this one's 400 ohms. Very suspicious. Look at all these blue tantalums. But usually when they fail, they go dead short. And it was just, which one was it that blew up? This one right here in the middle. Okay, so this middle one is our problem child. So one side is ground, the other side is 15. Let's figure out where it's going. There it is, right there, that pin. So yeah, as I suspected, that's the yellow wire. That is the 12-volt rail. It's almost always that these are 16-volt rated, and 12 volts is just a bit too close for comfort, and they will short out. It's probably not shorted anymore. It probably blew itself open, but I'm going to remove it from the board anyways. So same as before on the other motherboard, we'll just need a good amount of heat in that area, just because there's a big ground plane that one of those pins is hooked up to. So with heat, that was super easy. That just came right out. This power supply, by the way, it is designed for Pentium 4, so it's quite beefy on the 5-volt rail and also beefy on the 12-volt rail. So this thing can definitely blast things open like that, and it protected itself. It doesn't get hurt from that. Okay, let's see what happens now if this turns on. Okay, so All the rails look good. That's normal behavior. Remember, we don't have the crystal in here, so this system can't possibly work. Now I'm going to turn it back on and notice that the clock light will not be on, and that's because the oscillator is missing entirely. And the thing never comes out of reset either. It stays in reset. Incidentally, nothing on this motherboard uses 12 volts except for ISA cards, so not having this in is not a problem. So let's go for this 50 megahertz oscillator so we run the system at 25 megahertz, kind of to give it the best chance of running. And that socket's good, even though I didn't trim the legs. It's a nice firm connection. Look at that, it's not coming out. Right, let's see what happens now with that in there. Oh no, no difference. Okay, not all is lost. We don't know if these jumpers have been messed with, so I really need to compare the jumpers on this board with the photos on RetroWeb. Right off the bat, these two are unpopulated, but on the RetroWeb, they are. So let's get those populated. And I'm gonna match the 33 megahertz one that's in the photos, and then we can do the 40 megahertz if I can make out the jumpers. I'm half wondering if these jumpers and the other ones set things like the stuff that is available in the BIOS on the other one, like the ISA multiplier and stuff like that. All right, and then we have these jumpers. This is configured exactly the same as the photograph. This is the clock chip, so that one's set, that one's not set. And then these two jumpers in the photo, they're opposite, so they're both towards the middle. So I'm just gonna replicate that, and then we'll see if that makes any difference on this system. It could easily be that there's other damage on here. It could also be that this crystal oscillator is bad too. I should probably test that. Well, let's see first of all if this made any difference. So right off the bat, one thing that's weird is there's no clock light. Also never comes out of reset. And I think we're gonna have to try a different oscillator just for fun. I popped in a 36 megahertz one, so what, 18 megahertz if this works? No, no difference. Interesting. So for comparison's sake, let's see what this does. Okay, so the clock only comes on after it comes out of reset. So it has nothing to do with the oscillator itself, because if I remove the oscillator, obviously this system is not going to work. So I pop that out, and we turn this on. Here, it looks exactly like it does on the other one. Well, I just put that 50 megahertz oscillator that was in the other one that would run it at 25 megahertz, and there we go. It's running. Yep, it's slower because it's running at a slower clock speed, but that clock light comes on, but it only comes on once it comes out of reset. Ah. Now, in case you think there might be a problem with the BIOS that's causing this, that is not the case. The BIOS isn't even running at this point, and it doesn't need to run for the system to come out of reset. That is a hardware issue. Now, could be this microcontroller. I'm pretty sure this has something to do with the reset, and maybe battery leakage has caused an issue. So one thing that's different between this motherboard and the one in the picture is that one does not have this jumper, ADS delay. And I'm wondering if it needs to be on one of these two positions for the system to work. So I have it on a random position. Let's see if that made any difference at all. Nope. Never comes out of reset. Now this is the keyboard controller, the keyboard BIOS. This is actually a microcontroller. I always think that this has something to do with the reset. And we can double check that by taking it out of the other motherboard and seeing if it has the same symptoms as this one. Okay, so system is working fine, just making sure. BIOS out. See if this has the same behavior. No. So it comes out of reset. Interesting, interesting. Now I suppose for completeness, let's put the Intel one that was from the other board into this one. Let's see if that does anything. I mean, the system is posting. I don't know if the keyboard's gonna work or not. Sometimes it has issues. It's not always compatible with every BIOS, but okay, obviously the system is, it's trying to run there. Kind of tells us that this chip is good and certainly not our problem. Back on this motherboard, if I push the reset, that doesn't do anything at all. It would normally turn a reset on if the system was working properly, but that doesn't do anything. Almost certainly the reset pins go directly into the main chipset, which is getting really, really hot. Oh yeah, that's not good. That's not good. This shouldn't be getting burning hot like that. I wonder if this is bad. It is burning hot. Let's take all the chips out that can be removed in case there's some shorting of the data bus going on or something like that. So the memory comes out, BIOS chip comes out, and we'll take out this clock chip as well since it's socketed and it can come out easily. Yeah, it's getting very hot. hot very quickly. And the funny thing is, when we saw that low resistance when we checked the ohms on this connector, that could easily be this chip damaged. I mean, the processor's getting warm too, but that's normal for 36SXs. It is running at 25 megahertz, so it shouldn't get that hot, but it's getting pretty warm. Wow, yeah, that's burning hot. Really, the question is, did something catastrophic happen to this system? Incidentally, I just noticed, take a look at that. We have a little bit of crusties in that socket. So that would be from the battery leakage. You see blue through that via, that's just my bench mat behind there. Everything looks so clean. It's so weird how there's just a tiny bit right there. But I am definitely feeling suspicious on how hot this chip gets when the board is powered up. I wonder if I have another 36SX board with this same ALI chipset. I should go look real quick. Okay, well, I went into my box of motherboards and I found this. This sure looks the same. Well, it's got some serious damage on there. And it looks like I painted it with nail polish. And that was, I must have done this so long ago. That was before I knew to Dremel that off. So maybe that's something that I really, really need to do. The layout obviously is different. This is clearly not exactly the same motherboard. I mean, actually not by a long shot, but I wouldn't be surprised if this is the same chip under here. It's got this sticker on there, and this thing is interesting because it actually has a clock generator. So instead of a regular oscillator, it's got jumpers and a chip that's doing it. It has one of those 46 chips on here in the same package. I don't know if this works or not. I mean, oh yeah, look at the damage on the bottom too. But I kept it, so I assume it works. Before I go peeling that sticker off, let's power it up, see if it still functions even with all that corrosion there. All I really need to do is plug in the post analyzer card. That's what we need to do just to see if it does function. Here we go, 3, 2, 1. That's weird. I think I have, it only had 12 volts lit and nothing else. Did I have bad connection? Oh, I had bad connection. And it's posting. Wow. It's like the 12 volt rail is bad on this board. Maybe there's a bad trace, but that's not enough to keep it from posting. It's definitely posting. Okay, so I hooked the speaker up. That's what it's doing. It's complaining there's no video card. So I really do think this thing works. As bad as that looks, it totally, totally works. The sticker's kind of ruined anyways, so I think it's time to scratch that off so we can look at what's underneath it. I'm going to use the little plastic scraper here. There's a couple things I'm trying to do here. If this is the same chipset, we can use this motherboard to figure out some of the signals. But beyond that, I can also see how hot this gets, and we can measure the current on the power connector just to get an idea what the resistance should be. Because if we're getting that, oh yeah, okay. So this is not the same. So that sucks. So this is not a good test. Well, I was going to say, if it were the same, then I could use this to check for the resistance. We could see the signals, things like that, but clearly not. That's unfortunate. All right, just for giggles, let's take a look at some of the resistance on this motherboard anyways. 1 mega ohm. This one's really high as well. It's like way up in the kilo ohms there. 10 mega ohm. Wow, okay, well, so something, it does seem wrong. At the beginning, I was like, oh, there's nothing wrong. I think I was wrong. All right, this motherboard's way higher resistance. Yeah, okay, I'm on the ground there. Okay, well, there we go. Well, one thing is for sure, I really need to try to clean this up. I shouldn't have painted nail polish over that. I obviously did this an indeterminate amount of time ago. So what I'm going to do is I'm going to try to get that nail polish off. We'll just use a little acetone here. Should take it off for the most part. And then I can use the polishing bit to try to Dremel that away. All right, I've cleaned up the top side a good amount. And on the back side, we have at least one broken trace there. Everything else, well, those, I gotta file those away a little bit more. Everything else looks like it might not be broken. I wonder why we didn't have the minus 12 volt. I figure out which pin that is exactly. That's definitely a battery connection that is broken there. It is quite amazing this board works. We didn't actually try it out. I mean, we saw it posting, but we didn't actually go any further than that. But I'm pretty sure the fact that I put this away in my box of motherboards, I'm sure this board just works, even with all this horrible corrosion on here. Well, this video really went off track. I was supposed to be focusing on fixing this motherboard, not a third motherboard. Either way, I ended up sort of scraping away and getting rid of all of that corrosion that was on this side and on the back side. And I even swapped out the keyboard connector, and that's because, yeah, it was looking pretty crusty. So this keyboard connector actually comes from that motherboard I blowtorched. And to get it on here, I had to do a little bit of modification just because the little holes were slightly different. So a little offcut made this thing nice and strong. What we need to do is just make sure this motherboard is still working after this cleanup work I did, and actually plug a keyboard into it and make sure that I can get this thing to boot into DOS. Let's see if it still posts. All right, well, I think there's a bad connection in that slot. That was the one I plugged into before and had some issues with. Let's just try this one. We heard it beeping though, and there's no video card, and that means that almost certainly this thing is posting. Yep, there it goes. And we have all of those voltage rails as well. So I think the issue with the voltage rail was just a bad connection in the ISA slot. Probably a little deoxit in those slots might help that contact issue. Let's see what happens. Ah. Oh, weird that it gave us that long set of beeps, and yet it's obviously working. CMOS options not set, display type mismatch. I wonder if there's a jumper setting I need to set on here. That's kind of an unusual pattern there. Let's see if this is a contact issue. Okay, no beeping. Our display type still mismatched. Well, at least looks normal there. I think it's complaining because the default configuration of the BIOS on this motherboard must be CGA or something, and once it boots up, it realizes it's EGA and it changes this option. There's clearly no battery on this machine, and the date is just sort of random, which is totally fine. We'll just put it to something there. What do we have here for settings? Ooh, we have some interesting stuff. Write wait state, RAS precharge time, RAS to CAS width, refresh rate burst, AT bus stepping. Don't know what that is. Cyrix cache. Well, this is not a Cyrix chip, this is a TI chip. I don't remember if they're actually the same or not. That chip is very hot, by the way. The chipset, on the other hand, not hot at all. Fast reset, don't know what that is. I'm gonna turn the cache on just for fun. Save this, and I'm gonna have to plug in video card. Memory size mismatch, that's okay. That's probably because the caching, usually you just have to go and save it one more time, and that error should go away. 4 megs of RAM. There we go. It's booting 33 megahertz. I'll be curious if we can overclock this thing to 40 and then compare this to that original motherboard. Okay, I just popped in the disk controller card. Let's see if we can get this thing to boot. If it doesn't recognize it, I'm going to blame that slot is bad. Yeah, I didn't even see the BIOS. I'll move this card to the leftmost slot, furthest away from that battery leakage. Ah, yes, there the BIOS is now seen. So this slot's definitely dodgy. Maybe I have to steal another one off that blowtorch machine. Hey, look at that, booting right up. Keyboard is obviously working on this thing. This computer totally works, even with all that damage. It's totally fine. I mean, other than the dodgy slot. While we're here, I'll just run the quick benchmarks just so we can compare this motherboard at 33 megahertz to those other ones. Okay, benchmarks complete. So what we're looking at here is the 40 megahertz 36SX. This is the one I always use that's been working the whole time. 61 megahertz, and the characters per milliseconds is 5228. First result on this 46SLC, the characters per millisecond is quite a bit slower, so that's going to have an impact on things like Doom and also disk benchmarks, and that's just because this thing doesn't appear to allow you to overclock the AT bus speed, so it's probably stuck at just 8 megahertz all the time, or it could be even a little bit less than 8 megahertz. Now CPU speed 61 megahertz and speed 600, but on this machine 138. So in this particular benchmark, big difference. Next we have cache check. We had 8K of cache on the 36SX. It got 53 and 93 for the speeds. And down here, main memory speed was 11.8 at 89.0 nanoseconds per byte. So again, we have a relatively sizable speed increase on the 46SLC board. Now, one thing that's interesting is it only has 1 kilobyte of cache. So you can see this first column is 41 versus the 53 for all 8 kilobytes. And then after that, everything is 64, and it was 93 on the original board. And the main speed is 17.2 megabytes per second at 61 nanoseconds per byte. And of course, that's 89 and 11.8 on the 36SX. So the RAM speed also is significantly faster. And then finally, we have the Doom benchmark. On the 36SX, I was getting 17.0 frames per second. And on the 46SLC, 15.7. So it's worse. Now, this is with the 46 board running at 33 megahertz, but isn't that interesting? Now, I think a lot of that comes from the fact that the ISA bus transfer speed is so slow compared to the 36SX. That makes a big difference when you're trying to push pixels on an action game like this. Without a doubt, if you're doing something that's computationally intensive, the 46SLC is going to be faster. But a lot of time in Doom is spent pushing pixels to the video card, and that's where the ISA bus speed makes a big difference. Now, what I ended up doing is just changing the jumper on the little crystal oscillator on the 46 board here and overclocked it to 40 megahertz. And that's what we have on this second benchmark. So this first one here is when it's running at 33 megahertz. You can ignore the clock speed, 138. And after overclocking, it became 167. Now the video speed, 4012 on the overclocked one and 4045 on the other one. I think that's just margin of error. So no real difference. Now, cache check again had a pretty nice speed up. The 1K of cache went all the way down to 34 versus 41, and then that 64 turned into 53, which incidentally I think is the speed of the cached memory on the 36SX. I think it was getting 53 as well. And main memory speed is 20.9 megabytes per second at 50 nanoseconds per byte, and it got 17.2 at 61. So yeah, we had a nice little speed up just from that little overclock from 33 to 40. And to do that overclock, all I did was move this jumper from the left position to the right position, and that overclocked it to 40 megahertz. I did add a little heatsink on the CPU. I'm not sure that's actually necessary, but I just stuck it on there anyways. And that brings us to our Doom benchmark. So this is the original benchmark at 33 megahertz, and after overclocking it, 17.38. So it's sped up to about the same speed as a 36SX. So these benchmarks definitely show that the 46SLC brings the horsepower to the CPU computationally, but the ISA bus speed on this motherboard is a real hamper compared to the one that can overclock. And on the one that could overclock, I could actually push it further if the disk controller could accommodate it. The video card, this video card I'm using, I know can go even faster than the 13 megahertz it's at now, but it seems like this disk controller card does not like it. But other cards I've had do work fine at, I think, 16 megahertz, and that'll push the benchmarks of Doom even faster. Incidentally, I did have to upgrade to 8 megabytes of RAM on this board so I could run Doom. It would give a memory allocation error with this original memory in here. And the whole time while all the benchmarks were running, the CPU got very, very hot. In fact, it was kind of burningly hot, but the chipset on here really never got hot at all. So it appears that this SARC M396F version 2.7, even with all the battery damage, is working just fine. And all I'm going to do now is just put on some clear lacquer over this mess here so that it will not corrode any further and it will look a little bit more shiny since using that polishing bit sort of dulls down the solder mask and everything. Just amazing. This thing does work perfectly though after all of that corrosion. Just stunning and amazing. And one thing I should have done with this board when I worked on it the first time, whenever that was, I should have put a tick mark on it just to say that it worked. I should have done that. So finally, full circle, we're back on the motherboard that was the focus of this video originally, and I want to do a few things that I said I was going to do and I haven't done yet. Let's power this up and check the clocks. Make sure that we're getting the clocks, and maybe we can even find those somewhere on the pins that go into this main ALI chipset. All right, motherboard's powered up. Let's see if we can find that 40 megahertz signal. We should have 5 volts going into this, which looks like we do there. Should be ground on a different pin, which is probably that one. And then this one should be the output. Let's change the time base here. There it is. Yeah, I was just set incorrectly. This 9 kilohertz is, that's kind of an unusual thing. What I'm gonna do is I'm gonna take the crystal out and we're gonna measure that pin again. Let's just see if we see that same 9 kilohertz on there. No, not seeing anything. Okay, I think what I was seeing was aliasing. That's definitely something you have to be careful of when you have scopes like this. So we're gonna keep zooming in. And there we go. So 10 nanoseconds is the limit of this thing, and now it says 50 megahertz. And it's having trouble reading it, but it's because this scope's not really designed for frequencies this fast. So let's swap to a slower crystal. Okay, what's in there now is a 28 megahertz crystal oscillator. And there we go. So notice it's not having any issues anymore. I think we're at the edge of this scope's ability to check that or read that frequency. But 28.3 megahertz is spot on for what this crystal is actually doing. And that would make the CPU run at half of that. So about 14 megahertz or so. And I'm positive that if we plug in the post analyzer, we're not going to see any activity. It's going to look exactly the same. Yes, it is. It's never coming out of reset. It's not generating any kind of clock. Now we know from my other 36SX board that if we remove the crystal oscillator, the system looks just like this. It never comes out of reset. So what we really should probably check is that there's continuity from either side of this resistor. Who knows which side of it makes its way to this chip. But we need to make sure that there's some kind of connection there. Right, I ended up finding that particular signal actually goes to this VS. So it does go through this 33 ohm resistor. So on this side, we're at 0. And that makes its way right to the chip right there. So we know that the signal is getting through to this, through this resistor. And I did check to see if this oscillator goes anywhere. It doesn't seem to go anywhere except to the math coprocessor. It looks like it goes through this 33 ohm resistor and it goes right to there. I don't think that signal makes its way to the ALI chipset. It's just very difficult to see because, of course, I don't have the schematics and there are a ton of traces on this board. So we know that this oscillator is working, it's getting its 5 volts, it's generating its clock, and it makes its way to the main chipset. And yet the chipset doesn't come out of reset. Let's check to see if this 14 megahertz crystal is working. Okay, so system is powered on. The shape is not perfect. Oh, power supply shut down there on its own. Now you saw that there was a clock there. Did we have something else short on here? Just checking to make sure there's nothing on the bench that could have shorted it. No, there's nothing there. Well, we might need to get the thermal camera out to see if there's another shorted tantalum. It's quite possible there is, and that's causing the power supply to shut down. Well, I'm busting out the top-down thermal camera, the TC004. One of the things I was really hoping I could do with this camera, and it seems to support it, but I can't get it working, is connect up a USB cable and actually have it mirror this to my capture setup. So I'd be able to just overlay this on screen. Doesn't seem to work though. It's got an SD card so I can save images that I take and then little video clips onto the device itself. But it would be really good if I could just feed it directly into OBS. Okay, system is currently off and these two chips are still warm from before. Let's turn this on and I'll see what gets hot. Wow. So the power supply isn't even turning on now. All right, yes, we do have another short. And looking at the colors, it's the brown wire. So I think another tantalum has failed on this board. And it's this one right here. We have the same resistance value on both sides of it. Pretty sure that's a minus 12 volt rail. No, you know what? I took out the wrong tantalum. We still have a short on that rail. Now the reason why this didn't blow up like it did on the 12 volt rails is because the minus rails on the power supply doesn't have enough current to blast it open. Now I'm pretty sure that we have additional tantalums on 12 volt and minus 12 over here in this section. That's probably a 5 volt one. So I need to find those, and I didn't use my troubleshooting skills to identify the actual short. So the way you want to do this is you want to look for the lowest resistance. So we're at, what, 0.36 right now between the 2 points of that one I just removed. And then this one here, 0.4, so it's a little bit higher. So it's definitely not that one. And then we have another one probably right here. 0.33, it's gone down a little bit. And let's go back to that original spot over here. See, it's a bit higher. So it's this one over here that I'm gonna assume is our issue. Ultimately, you need to go through and just check to see if there are any others on the board. See, there are some down here, but I'm pretty sure these are gonna be 5 volts. Generally, the 12 volt and the minus 12 volt rail only runs up here on this part of the ISA bus. There is no 12 or minus 12 over on this section, so it doesn't make sense they'd put a tantalum down there. Okay, that one just fell out pretty easily. Heat makes all the difference. Let's just double check we don't have a short here any longer. We do not. It is just open. Perfect. And there is the specs, 10 microfarad, 16 volts. Go kind of as I said, 16 volts is just a bit too close to 12 volts. It seems to cause issues. But just like last time, there's no way that those shorted tantalums would have any negative impact on the operation of the CPU and the main chipset. Something else is wrong with this board. And this will be evidenced by the fact that the system will not work still in exactly the same way. All right, so I have the thermal camera out again. I'm going to see if anything is getting hot on here except for, well, the CPU and the chipset. So currently what the thermal camera is telling me is that this chip is at 65 degrees Celsius, hotter than the CPU. Everything else on the board, like these Jelly Bean logic chips everywhere, are fine, not too hot. We're up to 67 degrees on the main chipset now. There's a photo. The red mark is the 59 degrees Celsius. Now, this was after I turned it off for a minute. That's why it's cooled down from the 67. I just don't think that's right. It is not correct that it should get so hot. And this just leads me to believe there was a catastrophic failure on this board that ended up damaging the chipset, or it just died internally on its own. Only thing I have left to try, since I don't have another one of these motherboards to compare against, is I'm just going to remove the CPU from the board, and let's see if removing the CPU somehow makes the chipset not get hot anymore. Maybe the CPU failed and it's all shorted together, and that's somehow causing this issue. Although I don't think that's the case, because I went around various pins on the CPU and I checked to see if there were shorts. I did this earlier, and there isn't. You know, address lines, data lines, whatever. Yeah, there's nothing out of the ordinary at all. In fact, if we switch this to regular resistance mode, we'll see that it's pretty high resistance on all these various pins. Okay, well, not that high. 460, there must be a pull-up or something on there. You know, 20K ohm there, 10K there. Let's just try a couple of the random pins. You know, there's mega ohm on that. And you can tell these are definitely connected directly from the CPU right to the ALI chipset. This thing is a bus arbitrator, and the ISA bus, the RAM, all of it goes through the chipset. The CPU is just connected directly to this, and then all the other things on this board come through the chipset. It even generates the chip select for these various ICs, and these are bus transceivers, for instance, almost certainly for the data bus lines that go to the RAM, and these are going to be driven directly from the chipset as well. It's handling everything. It's orchestrating the entire operation of this motherboard. Now, if the CPU were dead short, say, and was somehow causing this to get super hot, I think we would see problems on the pins to the CPU, but I just don't. All these signals, they look fine. You know, mega ohm, K ohm, normal. I think what I'm going to do is I'm going to spend a moment, just go through all the tantalums that are on here and just check to see if any of these are shorted. They're all going to be 4.8 because I think they're all on the 5-volt rail. Yeah, none of those tantalums are dead short. Pretty much everything that's left, all the stuff that's down here, is all 5-volt rail, so it's like around 5 ohms. And this stuff is just used for probably the -5 rail, and there's a 5-volt one up here. I already took the 12 and the -12 out. That one was -12. That one's going to be -12, but that one's fine. So yeah, I just don't really know where to go from here. And I'm just not sure removing the CPU is really going to tell us anything, because there's just no evidence to show that the CPU is causing this issue. These CPUs always get hot when they're powered up. The other motherboard here has the exact same chip on it. Underneath this heatsink is the same AMD 40 megahertz chip, and it gets warm. In fact, why don't we do a test? I'll just pop this off. And what I want to test is I'm going to turn this on. Okay, it's running. Obviously, it's in reset. There's no oscillator. I just want to see if the CPU gets warm or stays cold. So far, it's actually totally cold. That's kind of surprising. Chipset's totally cold, but the CPU is cold as well. And on this motherboard, if I pop the crystal oscillator out, and we turn on the computer, let's see if these get warm, both of these. Yeah, CPU is getting very hot. So is the chipset. Okay, well maybe that tells me I should remove the CPU. I don't really have a good spare. I have this one, and I'm not even sure what kind of processor this is. It's obviously the same package. I don't know if that's an SLC 486 or what, but yeah, the CPU is burning hot. Well, I suppose what we can do, like I said, let's take it off. I'm going to use hot air, and then we'll see if the chipset gets hot. If the chipset stops getting hot, then maybe the CPU is doing something wild and causing it just to short the chipset. So I gooped on a whole bunch of flux, and I'm going to just start heating the board, and hopefully I can get this off. I've taken these off before, and they're not impossible to remove. It just takes time. All right, there's the chip removed. I just cleaned up the pads a little bit, but everything looks fine. Nothing got ripped off, and the chip should be fine once it cools down, if the chip is not damaged. I'm just going to give the motherboard several minutes to cool down and come back to room temperature, and then I'll probably clean up some of this flux that's all over the place, and then we'll give it a test. So the first question, with our CPU removed, do we still have 5, 6 ohms, whatever, between ground and 5 volts? We have 11 ohms, so it's gone up a little bit. But that still seems too high, and it makes me think that maybe the CPU was damaged, and so was the chipset. Both were damaged. And I think our big test will be, let's power this thing up with no CPU or crystal oscillator, and let's see if the chipset gets similarly hot to what it was doing before. Okay, the system is running, and yes, immediately getting super hot. Just for grins, let's put the oscillator in. Let's plug in the post analyzer. Let's just see if it tries to come out of reset at least. This doesn't even know the CPU's there, I don't think, until it comes out of reset, and then the CPU should start doing stuff. So if it doesn't come out of reset, there's no way the CPU could ever do anything. And yes, not coming out of reset. And there it is, just so you can see in real time, the CPU, or the chipset that is almost 70 degrees Celsius, and it's only been on for, what, 30 seconds? I mean, it's up to 70. That is not right. It should never, ever, ever be that hot. Oh dear. Well, unfortunately, I'm going to take my crystal oscillator out of here because I think at this point, this is going to be a parts board. The fact that the chipset gets to 70 degrees Celsius without a CPU installed, without a crystal oscillator, pretty much condemns this board to parts status. Maybe at some point in the past, the power supply connected to this sent like a power surge into the 5-volt rail and took out the CPU and the chipset. It was weird that the CPU also was getting super hot when the oscillator wasn't installed, because the AMD CPU motherboard wasn't doing that. Pretty much tells us that I think that CPU is also bad. If you're watching and you happen to have a 366X board that has the same ALI chip, if you could comment down below and let us know what is the temperature of the chip after it's been running for 30 seconds or a minute, and also what is the resistance between ground and 5 volts. Be really curious to be able to compare another ALI to this board, and knowing that information would obviously allow me to fully condemn this board, because until then, I don't know, there's somehow a possibility there's something else wrong on this board. Maybe people watching have an idea of what might be wrong with this board that's causing this chip to do this. So unfortunately, I'll have to end the video here. You kind of win some and you lose some, and not everything can be fixed, especially when you're lacking schematics or lacking data sheets and it's using a custom chip like this ALI chipset. There is not too much you can do, and I don't think it's even cost effective to, say, try to replace this ALI chipset unless someone has another one of these boards that's got this chip on it and has catastrophic damage from battery leakage. I must say that swapping a chip with this many pins would really push the limit of my surface mount soldering skills, but I suppose it'd be worth a try potentially. But on the other hand, I'm also not convinced that this CPU that was on here, which is sitting over there, is actually good. And that extra CPU I have, I don't know if that one is good, and I also don't know if it's a 46 SLC. I don't know what kind of configuration changes you need to do on this board if that is a 46 SLC. This chip has a little epoxy bonded heatsink on it, which unfortunately you can't really get these off. It's very destructive to try to take those off. So that's why I don't even know what that chip is. So there we go. If you like this video, I'd appreciate a thumbs up. Sorry it didn't really lead to a repair, but that's just how it goes sometimes. And if you didn't like this video, you know exactly what to do. Comment down below if you have thoughts on this. Thanks to my supporters. Names go up the side of the screen. And I think at this point, I need to really clean up the basement down here. And I have to get to working on the Lisa again. I got to get that machine finished, and it is now time. So watch for those Lisa videos in the future if you're looking forward to them. If not, you can always check out the second channel or some of the older videos in the catalog. I'm sure there's something interesting to watch again. And I guess that's going to be that. So stay safe and stay healthy, and I'll see you next time. Bye.